As we begin Unit 6 on multiple representations, we'll be doing a little bit of algebra. In this video I'm going to go over how to solve 1- and 2-step equations. At first, algebra will seem a little pointless as the cartoon below implies, but there are real-world applications, and at minimum for now, you're going to need to know how to do algebra so you can do well in your math class. Before we go on to learning how to solve 1- and 2-step equations, I wanted to quickly review what an equation is and a couple of its key features. An equation is a statement in mathematics that says that two things are equal. An equation will always have a left side and a right side, and will always have an equal symbol in between those two sides. An equation is saying what's on the left side is equal to what is on the right side. It is useful to think of an equation like a balanced scale that you see here in this image. What is again on the left side is equal to what is on the right side. An equation that is not balanced is not true and therefore is not an equation. For example, if I were to add 1 to the right side of this equation would now be unbalanced. I know this because 1 plus 1 equals 2, and 2 plus 1 equals 3, but 2 and 3 are not equal to one another. However, an equation will remain balanced if I make the same change to both sides of the equation. So if I add 1 to the left side of the equation, and I also add 1 to the right side of the equation, this equation will remain balanced. And we can see this because we know 1 plus 1 plus 1 equals 3, and 2 plus 1 equals 3, and 3 equals 3. The key point to note here is an equation will remain balanced if I make the same change to both sides of an equation. In the last example I showed you, I added 1 to both sides of the equation and kept the equation balanced. I could also multiply, for example, both sides by 3. So here I would do what's in the brackets first, and I would get 3 times 2 equals 2 times 3, and I would then see that both sides are equal to 6. I could also divide both sides by 2 and keep the equation balanced. So if I do 1 plus 1, I get 2. And so I get 2 over 2 equals 2 over 2, and both equal 1. Way back in Unit 1 when you were learning about the Pythagorean Theorem, you were already applying this principle that an equation remains balanced when you make the same changes on both sides of the equation. So we're just going to run through an example of the Pythagorean Theorem so you can see how you've already been applying this principle. If you recall, and you can see in the cartoon here, the Pythagorean Theorem is a squared plus b squared equals c squared. So we'll write out our formula. And then for our purposes here, we'll label this side A and this side B. And we're using the Pythagorean Theorem here to figure out what the side length C is. And so since A is 3, we'll do 3 squared, and B is 4, we'll do 4 squared, and that equals C squared. And then we know 3 squared equals 9. 3 times 3 is 9, and we know 4 squared is 16. 4 times 4 is 16. And then we write down here C squared. And then we get 9 plus 16 equals 25 equals C squared. Now to solve what C is, we would need to square root C squared in order to just be left with C. However, if we square root C squared, in order to keep the equation balanced, we will also have to square root 25. So if we square root both numbers, we'll keep the equation balanced, and we will get the answer 5 equals c. So now that we know that an equation must always remain balanced, we can move on to learning how to solve one-step equations. The key strategy for us here is to isolate the variable. We can isolate the variable by rearranging the equation so that all the known numbers are on one side of the equation and the unknown variable is on the other. In the example we have here, we can see that on the left side we have a variable and a known number. On the right side, we have a known number. Using what we have learned about keeping an equation balanced, we can isolate the variable x on the left side by subtracting 4 from both sides of the equation. So it's very important that you follow this part of solving the equation, at least in the beginning while we're still getting used to it, of actually writing in the minus 4. So we can see here we have x plus 4 minus 4 equals 6 minus 4. Well, 4 minus 4 equals 0, so on our next line we're just going to write x. And we know that 6 minus 4 equals 2. So x is equal to 2. We can then check our work by replacing x in the original equation with 2. And writing out the equation and checking that it is true. 2 plus 4 does equal 6, so we know that we've correctly identified that the variable x equals 2. Alright, so with this example, 4 plus x equals 6 is the exact same question we were just working with. However, I switched the order on the left side and put 4 plus x instead of x plus 4. And I'm doing this simply just to show you that when there is no negative sign here next to the 4, we can assume that it is a positive, and when we assume that, we then know that we have to, in order to isolate the x on the left side, we have to subtract 4 from both sides. So I'm just going to walk you through that as well. So you would have 4 minus 4 plus x equals 6 minus 4, and again 4 minus 4 equals 0, which would just leave us with x on this side, and 6 minus 4 equals 2, x still equals 2, and I want you to get used to this idea of checking your answers each and every time. So 4 plus 2 equals 6, and we know that's correct, so we've done this correctly. Now, what if we had a negative 4 on the left side instead of the positive 4 as we did in the last two examples? In this case, we have to add 4 to both sides in order to isolate x on the left side. So I'm just going to walk you through this one as well. Negative 4 plus x equals 6 plus 4. And then negative 4 plus 4 equals 0, so we're left with just x. So x and 6 plus 4 is 10. X equals 10. And if we check our work, negative 4 plus 10 equals 6, we will see that it is correct. When solving two-step equations, you're going to want to follow the same strategy of isolating the variable, which means you have to rearrange the equation so that all your known numbers are on the one side, in this case the right side, and all your unknown variables on the other, in this case the left. So let's do that first like we've been doing so far. So we would have 4x plus 3 minus 3 equals 11 minus 3. And if I do that, then 3 minus 3 is 0, so I'm left on this side with 4x equals 8. As hopefully you will recall from the previous video that I posted on the website, and you should have watched, this 4 and x next to one another implies that the 4 is being multiplied by whatever the value is of x. In order then to isolate x on the left-hand side, I'm going to need to divide both sides by 4. And I'll go ahead and do that here. Divided by 4, 8 divided by 4. And once I do 4 divided by 4, that equals 1. 1x is the same as just writing x. And if I do 8 divided by 4, that gives us 2, and therefore x is equal to 2. And we check our work, so 4 times 2 plus 3 equals 11, and 4 times 2 equals 8, plus 3 equals 11, and we know that that's correct. Therefore, we have solved this problem correctly. Alright, another example, 64 minus 2x equals 58. So again, I want to put on my right side, since my variable is already on the left, all of the numbers that I know. And so I'll do that now. I would get 64 minus 64 minus 2x equals 58 minus 64. And then I would end up with negative 2x, 64 minus 64 equals 0. And I would end up with negative 6. 58 minus 64 equals negative 6. Now to isolate this, the x on the left-hand side, I'm going to have to divide. In this case, I'm going to divide by negative 2, and it's important we keep our negatives and keep track of them so that we can end up with the correct answer in the end. Negative 2 divided by negative 2 is going to just give us positive 1, and 1x is the same as just saying x, so I get x. Negative 6 divided by negative 2 is going to give me positive 3, so x equals 3. Then I check my work, 64 minus 2 times 3 equals 58, and 64 minus 6 equals 58, which is correct, so I know that I've solved the problem correctly.